Now, the three things that you need for a viable hydrothermal resource are heat, water, and permeability. You need to be able to move the water around inside the rock. And so for Hawaii, and I'll focus on the Kilauea East Rift Zone at this point, the heat is obviously in the magma, and we know where magma moves because we understand what magma comes up underneath the summit and moves out laterally in the rift zones. So that's the first place we look for the original magma source. And I'm using the lava flow hazard zone map here to indicate rough delineations for where the East Rift Zone boundaries are. I've also plotted mapped fissures and cones and cracks within the East Rift Zone to give you an idea of the variety of pieces of the rift zone and the various expressions of it. The second piece, since we've got the heat covered, we also need water to be able to transport this heat. As yet, there is no really economic way to extract heat directly from rock and generate electricity that way. So you need a medium, and water is a very convenient one to do that. In Hawaii, there are several different ways that you can find groundwater. The most common one in all the islands is the Guyman-Hertzberg lens, which is fresh water floating on salt water. It's very prevalent around the coastal areas of most of the Hawaiian islands. Also important are dike-impounded groundwater. So within all the rift zones, we have a bunch of dikes coming up, and in the older islands in particular, those dikes tend to impound water from going out towards the ocean. So water levels inside these dike compartments can be quite high, several hundred feet. And then the third way, the third general way that we find water is by it being perched on ash layers. Of course, all the water starts off as rain, percolating down through the matrix of the island. And so as it comes down, it can get trapped on higher perched ash layers, or it gets down into the sea level area and floating. It will be floating on salt water at that point. On the right is a map for some work that the U.S. just did in the in the 90s, where we sampled a lot of groundwater sources in eastern Hawaii Island, and we coupled that with rainwater catchment samples all over the island, all different elevations and such, and we matched isotope signatures so that when we sampled the groundwater, we could tell at what elevation the rainwater fell at. And so the black lines that you see here are attaching the elevation of the rainwater that eventually migrated into that groundwater source. And you can see that the general patterns are basically deflected by the rift zones. And that tells us again that these rift zones include dikes that don't allow water to flow straight through them. They flow around them basically, or if rain gets captured inside a rift zone, it'll be stored as a high level water source, it's called. The blue lines are rain contour lines. And so the high level and the little round blob in the upper part of the diagram is a high rainfall area that extends down from Hamakua. So that's a major recharge area. And we used to work with a hydrologist in Honolulu several years back who did the initial groundwater assessment for this side of the island. And he was telling me that the total outflow of water between Hilo and Pohoa, actually between Kea'au and Pohoa, was on the same order of magnitude as the outflow of the Amazon River. It's huge. South of the rift zone is not quite so good. In the last 15 years or so, based on a set of deep drill holes near the Hilo airport, another way of transporting groundwater has been discovered. And that is that at the contact between volcanoes, in this case between Mauna Loa on top at the Hilo airport with Mauna Kea just a few hundred meters underneath it, a drill hole going through the Mauna Loa-Mauna Kea contact can find large amounts of water trapped underneath the contact. So it's basically artesian water at that point. If you drill through that contact to hit that groundwater, it will have enough hydrostatic pressure to come out of the hole. That's an interesting notion that there are large amounts of water that come from fairly high up that are trapped that way and can come down to the lower altitudes. On the right side, I've cockroached a figure from another paper, recent paper, that shows how Kilauea probably formed on Mauna Loa. We've all known that Kilauea is a much smaller volcano than Mauna Loa. And it seems like every time somebody gets a new discovery, Kilauea gets even smaller. The upper figure shows 275,000 years ago, Kilauea just being born basically on the hip of Mauna Loa. And through the years up to present, you see that Kilauea is basically building almost in a little saddle on Kilauea, so that if you drove through Kilauea far enough, you would hit Mauna Loa. Just like at the airport, you drill through Mauna Loa, you hit Mauna Kea. Now, if you couple that with the idea that groundwater can be trapped underneath the contact between volcanoes, that may also be a possible source of deep recharge for some of these hydrothermal systems within rift zones. Well, one other thing I'll say, normally I'm thrilled to have questions while I'm talking, but because I have such an eminent set of co-authors, I would much rather you ask questions afterwards so that everybody can answer. Now, to go on with the water idea, this is a temperature profile obtained in the well right here at the summit of Kilauea. Again, it had some rather disappointing temperatures down at the bottom, at least compared to what they were targeting. But it had a very interesting shape. The first flat area as you come from the top is the water table. The water table is very high up here. It's about 700 meters above sea level. And so clearly it has to be impounded, because if that water were just sitting there in not too long a time, it would just basically flow through the rock out to the ocean. So it has to be held back somehow. And we think that's either, or more probably, dikes within the Kauai fault system, if not within either of the rift zones. So there's high level water up here. The drill hole went through the water down a little below sea level, and the top of the water table was quite hot. As it drilled farther, the water cooled off a bit. And so one of our colleagues in the USGS did a bit of modeling on that profile, because it's kind of an unusual profile. And he found that the profile itself is indicative of a response to a thermal event. Basically, this is a thermal profile that's not in equilibrium, as it were. It's still responding to something that happened. And the middle figure is a number of model curves for different years before the present. And the ones that you can read are 100, 800, and 2,500 years before present. So this work suggests that the water in the high-level system here is still responding to an event that happened sometime between 750 and 1,000 years ago. Now, couple that with these very interesting things that Don Swanson's finding out about the history of Kilauea and caldera formation and all of that, it's possible that that thermal event might have something to do with some fundamental part of the caldera development. So to kind of put all that together, the different areas of expected groundwater occurrences here in the East Rift Zone, at the top, around Mountain View, the Mountain View area and around Highway 11, we expect that most of the water will be perched, fairly shallow, which usually means that there's not a whole lot of water there to develop. Between Kīlauea and Pohoa, we have a very thick basal lens, very easy to develop water there. There are a number of wells tapping that basal lens along Highway 11. Within the dike zone, within the rift zone, there are dike-impounded waters. And in parentheses, you can see the rough ages of those things. The basal water between Kīlauea and Pohoa is relatively recent, probably 10 years, on the order of 10 years or less. The water on the south side of the rift zone is very thin, probably because it's cut off by the large recharge areas to the north of the rift zone. And that's also where we see thermal springs, or thermal outflows along the coastline. Also probably because they're not being overwhelmed by this large recharge area to the north. Those are of intermediate age. The dike-impounded water is obviously the oldest stuff. And we have sometimes quite a difficult time try to figure out how old that is. Now, permeability is the third part of this. We know that we have water, we know that we have heat. There's not a whole lot of permeability data, but I go back to the drill hole, the scientific drill hole up here, which did make some permeability measurements. There are the little black dots on top of the thermal curves. And I put handy little blue bars there to kind of summarize the information. The scale is on the bottom, which will make no sense to anybody, and it doesn't really even make sense to me, except that high permeability on the right, low permeability on the left. And so above the water table, permeability is quite high. And looking at the samples from that interval, it's very clear that if you try to measure the permeability of a lava flow piece, the permeability is rather low. But if you look at it in bulk, lava flows on top of lava flows that are cracked, permeability can be quite high. And so it's clear that the permeability in our subsurface is mostly in the cracks and between lava flows. It's not through the flows themselves. However, when you get below the water table, you find that permeability drops by several orders of magnitude. It doesn't go to zero, but it's quite a bit lower. And that turns out to be a function probably of the hydrothermal system that it has tapped. The water is hot, it can dissolve things off the rock. A lot of this water is fairly high in dissolved solids, it's acidic. And so as it circulates, as it cools, it tends to deposit things along the very pathways that it's traveling. And as it does that, that bulk permeability decreases. So why was the site that is now being developed for geothermal, why was that chosen? Aside from the fact that you can drive right to it. And so one of the main factors in the choice, there are a number of pieces of evidence that came together to choose the site for the HGPA test well in 1975, 74. There were several places on the lower East Rift Zone anyway where eruptions erupted differentiated lava. That was lava that had been sitting in the ground for quite a while. And of course that means that there must have been local storage in those places. Typically as the eruption progresses, the chemistry might change or something, but the initial parts were probably pushed up from something that was stored there. These three areas, Hehehulu, Kaliu, and Pu'unu'ula, in the East Rift Zone were such places that erupted differentiated lava. The ones with the upward pointing arrows are places where there were phreatomagmatic deposits. That would mean things that were cinders or fairly coarse ash layers or something. And that is direct evidence that water and magma have interacted in some sort of explosive eruption. So there were four particular places on this side of the volcano that had such evidence. Of course, the summit has a lot of evidence of explosive events. But there were also two in the lower East Rift Zone. One of them was in Leilani Estates, right across the street from the HGPA well site. As I said, there was a lot of other evidence. There was a clustering of earthquakes in that area even before the drilling started. And these two lower left graphs are a cross-section of the seismicity, which suggested that at least the north part of the rift zone, the faulting in the north part of the rift zone dipped south towards the ocean. And that fit well with an idea that Jim Moore came up with from HVO in 1965, where he was looking at the fact that there were a number of cracks and fissures in the northern part of the rift zone, but the cones and things were in the southern part of the rift zone. And that suggested to him that the rift zone itself had a bunch of faulting in it, but basically the trend of the faults was to the south towards the ocean. There was also what's called a self-potential anomaly, where they're very prominently in this area. Self-potential is a natural electric voltage that can be measured on the surface of the ground. And our best guess about why those appear in some areas is that it's generated by these hydrothermal systems, hydrothermal fluids moving in the subsurface. They have so much dissolved solids in them that they can actually generate electric potentials. at the Earth's surface. And also in the upper right, you can see that the hottest well at that time, which was just a well that went into the upper part of the water table, the hottest well was in this same area, and that was one of those 1961 test wells. So it was probably a good choice for the first drill hole to see what the resource was going to look like. And it turned out to be successful. It was about 2 kilometers deep, just short of 2 kilometers. And it told us many things about the resource. Of course, it was the first thing that ever sort of came back to us from the resource. I've tried to simplify this diagram a little bit. The blue areas on the bottom are the part of a well that indicated it was submarine lavas, and the browner stuff on top is what we call the subaerial stuff that was erupted in the air. We expect that interface will not be at sea level anymore because of the subsidence of the island, but it makes a big difference about the permeability aspects of the rocks. And then that little yellow box indicates the parts that are either partially or fully sealed by secondary mineralization, the stuff that mineralizes out of the hydrothermal fluids as it circulates. And then on the right, you can see the parts of the section that generated the resource, that actually produced resource. Most of it's right down at the bottom of the well. And so the idea here is one that's been around for a long time, that these hydrothermal resources will essentially seal themselves in, and that can allow some pressurization. But it's a handy thing for them to do. Oh, and up on the top, there's a little bit of a history of the HGPA well itself. It produced 31 megawatts of electricity for 8 years. I was just reading some of the news articles about the testing that started in 1976, and from probably the first or second test, there were already complaints of noise and hydrogen sulfide emissions from the nearby residents. So to go a little, follow the history a little bit more, once HGPA was successful, and it was very successful, private companies started to plant their flags. And so the first one that I'm aware of was a 250, should have been megawatt, sorry. I was fighting with PowerPoint this afternoon, and haven't got to be a K. But so this is this was Campbell Estate land at this time, and a private developer came in and proposed a 250 megawatt development in this area. You can see that the wells border very closely the national park boundary, and then in the colored bars here are their assessment of the volcano hazards for this parcel, the red being the highest volcano hazard, orange being the next. I think orange they claimed was high hazard, the red was highest, and the rest were low. This was, the paperwork was started on this in 81 and 82. The USGS took the position that this was a really bad place to develop because of the potential of volcanic eruptions. And of course, in 1983, Puna started erupting. They didn't immediately abandon the prospect, but when they did, they suggested a land swap with the state. So the Campbell Estate swapped this little parcel of land for the next one down rift, which was a forest reserve, the Wauakele Forest Reserve. And they proposed a 100 megawatt development in this area. And at that time, Puna lavas had already gone into their planned development, but they could kind of work around that. And True Pacific eventually drilled a hole kind of in the lower part, the downrift part of this particular prospect. And they hit a hot resource. It was quite hot, actually, but it didn't produce. And so they eventually abandoned it. The land was purchased back to the state, and it is now owned by OHA.